Hello there. Today we'll be talking about a couple of smart pointers that let us sort of break the rules. These are the RC and RefCell smart pointers. Let's begin. If there's something that Rustaceans learn from the compiler over and over again, is that values can only have one owner. However, sometimes that just doesn't cut it. For example, if we have a graph data structure, it's possible that we'll want multiple edges connecting to the same node. On the left of the screen now, you can see a struct definition for a node of a graph. Next, starting on the right, we create a box node instance called n3 with a value of 3 and pointing to none. After that, we create another node, this time called n2 with a value of 2 and pointing to n3. Moving forward, we create yet another node, called n1, with a value of 1 and pointing to n3. If we place these let statements inside of a main function and ran the code, we would get errors saying that the value of n3 was moved in the definition of n2, blocking us from using it in the definition of n1. This is nothing new, but this is just further evidence that we can't have multiple ownership without taking the matter into our own hands. And that's where the RC, or reference counting smart pointer, comes into play. It keeps track of the number of references to a value to determine if it's still in use, and if it's not, if it can be cleaned up. Now let's see if we can bring that graph example to life with reference counting. Okay, this is what we had from the previous visual. Let's make some changes. First, we'll bring our C into scope. We do that with use std rc. Next, we'll change from using a box node to an RC node. And now, of course, instead of saying box new, we say RC new. But a bit that you might not be expecting is that we'll have to add calls to RC clone and to our reference counter n3 multiple ownership shenanigans. So in here, instead of just sum n3, we say RC clone n3. We have to make this a reference, and then we can copy this bit and move it right here. You might be frowning at the clone call, but something important to note is that RC's clone does not make a deep copy of all the data. It only increases the reference count. Alright, with that said, if we run the code, for the terminal to load, cargo run, we'll see that everything compiles just fine, and we just get warnings about unused variables. But anyway, with all the talk of reference counting, I think it would be cool to actually see the count increase. We can do that by accessing a function from the RC type called strong count. So let's change our code to print the counts after the start and after every clone. Now, after the creation of n3, let's add a debug call. We'll say RC strong count, and again we'll pass a reference to n3. And now let me just copy this. Now, after the creation of n2, we'll add a debug as well. Oops, I think I added the semicolon in the wrong place. Did not close that properly. Now we let's move the creation of n1 actually to an inner scope. So we'll do open brackets here, close brackets here, and inside of here we'll add that same debug call. We're doing this to display how the reference count will go down after n1 goes out of scope. Now, to finish off, let's just make one last call to the debug macro, And now, bringing back the terminal, can cargo run. And okay, now running the code, we see exactly what we wanted. 1, 2, 3, and then 2 again when N1 goes out of scope. With that, we have ourselves multiple ownership, and we've broken one of Rust's most basic rules. Yay! Now let's move on to talk about RefCell and break some more rules. Alright, we've seen that we can use RC to have multiple owners of a single variable, and of course that's breaking a rule. Regardless though, we can sleep comfortably at night thinking that all is good because at least our immutable variables are safe from mutations, right? Or so you thought. RefCell breaks that rule by allowing you to mutate even immutable variables. So no more comfortable sleeping at night. So remember how the borrow checker makes sure that at compile time that we have either one mutable reference to a variable or any number of immutable references to a variable, but not both? So what RefCell does is it moves that checking to runtime rather than compile time. So if you break these rules, rather than just getting a compile error with RefCell, we panic. Okay, at this point, you might be asking, why would I want to move that checking to runtime if I failed regardless? And well, the thing is, as you've probably learned already, the Rust compiler is conservative, meaning that at times, if it cannot tell that a problem is memory safe at compile time, it will go with the safest option and stop you from compiling. If we, as a programmer, know best, though, we can take the responsibility away from the compiler and use RefCell. Alright, enough talking, let's see RefCell in action. Alright, so in this snippet of code, you see that we're making an immutable variable x, an i32 variable, with a binded value of 5. After that, we print its value with the debug macro, and next up, we try to increment its value by 1. Clearly, this will fail because cargo running it, we see that we cannot mutate an immutable variable. And that makes sense. Cool, let's break that. First, we'll bring RefCell into scope. We can do that by saying use std cell, RefCell. Next up, we'll wrap the value of x inside of RefCell new. And please note that we're keeping x as a mutable. Now we'll add a call to borrow x as mutable, and obviously, so this is a mutable reference. So now we have to dereference it to edit its value, incrementing by 1. Okay, you might be surprised to hear that this compiles. And while x is immutable, its value has been changed. Now, magic aside, remember how I said that RefCell would still respect the borrow checker, like not having multiple mutable references and whatnot by panicking? Let's make our code panic by deliberately adding another borrow mute. Okay, so I'll be adding a couple of unused variables. So I'll just add this little attribute here. Actually, I'll make this for the entire crate. I'll say allow unused variables. Okay, just so that we omit warnings in the output. Cool. Next, instead of incrementing the value, let's just assign it to a variable. So we'll say something like let first borrow, and we'll say x dot borrow mute. Next, let's add another borrow mute. So we'll say second borrow x dot borrow. Oops, I don't want to just borrow. I want to borrow mute. Okay. Now, running this code, we get failure, and that's great. That's exactly what we wanted. So, at the very least, we can still sleep comfortably thinking that while we can break the rules, we're still safely under the borrow checker's wing. Alright, next up, how about we combine RC and RefCell to doubly break the rules? Like Pokemon used to say, prepare for trouble and make it double. Due to the fact that RC gives you immutable access to data, it's very common to combine RC with RefCell to have mutable data with multiple owners. So to show how that can be useful, I brought back the graph example that we crafted before. Okay, now just to get it out of the way, I'll add and allow. This time we'll be allowing dead code, just to hide some of the warnings that I know we'll get. Okay, anyway, first things first, let's bring RefCell in scope. Again, it's an STD cell RefCell. Next up, we'll wrap our node with RefCell. Aside from RC, and actually before that, let's just bring, let's just derive debug here, so we can see the output when we're done. Cool. With that done, let's add a call to RefCell new here. That should be there. And prior to modifying anything, we will, let's just add a debug call here for N1, and a debug call here for N2. After that, let's modify the value to say N3, we'll borrow mute, and then with this borrow mode, we're accessing the value. And we'll set that to 1. Now let's print N1 again. And then let's print N2. Or rather, actually, reference of N2. Although that's the end of the program, so it doesn't really matter. But just force of habit. Okay, now running this, we see that... let me make this bigger because we'll have a lot of output. We see that, so the value was, so we have N1, value of 1, but it points to a node, which is N3 with value of 3. Same thing for N2, value of 2 points to a node, value of 3. And then, after we changed it, you see that now N3 is 1, N2 is 1 as well, and the value's been updated across all the multiple owners. Super neat. Next up, let's change gears a bit to talk a bit about a con or negative point in using RC and RefCell. At this point, I think it's important to mention two things. One, neither RC or RefCell are meant to be used in multi-threaded scenarios. There are other tools for that, which I'll probably mention in a future video. And two, with RC and RefCell, it is possible to create memory that is never cleaned up. That is, it is possible to get a memory leak, which is the topic of this section of the video. So to be more specific, a memory leak can happen when two items refer to each other in a cycle. So if you think about it, that creates a memory leak because the reference count will never reach 0. So let me show you what I mean, looking at the example we had before. Okay. First of all, let's delete n3 from the main function. Next, let's make n2 initially point to none. And let's wrap it in RC and RefCell new calls. So RC new and RefCell new. Let's go to the end and close two parentheses. Right? What are we missing? Oh, that's an extra. There we go. Okay, now n1 will point to n2 instead of n3. So n2, and we'll also wrap it in RC and RefCell new calls. Okay, next let's make n2 point to n1, so we can do that by borrowing mut, and then instead of changing the value, we'll say points to, and we'll get some RC clone n1. Next up, let's do some cleanup of this debug calls. We can delete these two, and the rest of the debug calls we can just change them to display the strong count rather than the node. So in here, we'll actually keep that, say RC strong count, and RC strong count. Alright, now running this code, it might seem innocent enough, right? We just get 2 and 2, the counts, which makes sense, right? And 1 exists, and that's the first count, and it also points to, it is also pointed by n2, so that's the second count, and then plus the same thing for n2. With that, let's try calling an std memdrop on n1. So let's make this smaller again. Now, right after the debugs, like I said, let's just add std memdrop to n1. Now, after this, n1 is moved, so we can't print its strong count anymore. In any case, let's just add a debug call to print the strong count of n2. Alright, now before running this code, what output are you expecting? I don't know about you, but I'm thinking 1, right? Like n2 is no longer pointed by n1 because he was dropped, so its only count should be itself. No? Let's see. And it's still 2. What's going on here? The reason is subtle, but what's happening is that Rust really can't drop that memory because n2 is still referencing n1. Now, of course, if we go to the code and before the mem drop, we add a call to take. So that is makes the points to option value none. So we say n2 dot borrow mut points to take. If we run the code again, we see that, chadam, the output is as we expected. Now, if you're not convinced, let's remove the stake call. And instead, let's just print the strong count of n2. And after that, we print n2. Okay, so what does it look like? If we run this, we see that we get this. Now, if that doesn't scream memory leak, I don't know what does. Now, let's talk about one strategy other than the premeditated take to fix this. This whole time, we've been showing the strong count of stuff, right? And with that, you might have wondered, why is it a strong count in the first place? Well, that's because there's also a weak count. And that's where weak T, that you saw in the title of this section, comes into play. We've seen that an RC requires a strong count to be 0 for it to be cleaned up, right? That's why we ran into the whole problem of the cycle thingy. The difference with weak is that that's not the case. It doesn't require its count, weak count, to be 0 to be cleaned up. Hence, with weak, you don't really have guarantees that the thing you're reference counting still exists. That is, in Rust speak, it might be none. That is, strong reference established a shared ownership idea. Weak reference doesn't express an ownership relationship. So let's make a couple of changes to our example to make use of weak and fix our problem. Okay. So first, now together with our C, let's bring in weak. Now in the definition of our struct, let's change from our C to weak. Now you might be thinking that with weak, we'll use weak new instead of our C new, but that's not the case. We'll keep it RC. So this part stays the same, and same for N1. But we'll see how we interact with weak. So instead of RC clone, we'll do an RC downgrade. And no magic here. All that it does is it gives us a weak reference. So the downgrade function gives us weak T. Now, of course, same thing for N2. So instead of RC clone, NC downgrade. Now, for the debugs, we know that the strong count will stay the same because we don't have any clone calls, right? It will stay 1. So the strong counts. So instead, we'll just show the weak count. And after that, we'll keep our mem drop, and we'll change the strong count to be a weak count instead. And we can keep the debug at the end, because I guess they'll show that we have fixed the problem. Now, running this, we see that we get 1, 1, and 0. And that's awesome. That's what we wanted. The weak count for N2 dropped when N1 was dropped. So now with the debug call to print the struct at the end, you see that one of the consequences is that we don't get to see the N2 value anymore. While that might be annoying, that's not the N2 value, the value the NN2 points to. And so I was gonna say, while that might be annoying, that's because it doesn't make such guarantees, right? The value is still there. So in fact, we know it's not, and we can check that by after our debug call. Let's make this small again. We'll add another debug call, but this time we'll do an N2 borrow. We'll get the points to. We'll make that a reference so that we can unwrap without taking, and then we'll upgrade. And what upgrade does is that it pretty much tries to follow that reference and returns an option. Awesome. Now running this, we see that we get a none. which is great. That's what we were expecting. Now let's just try commenting out this S3 memdrop and running the code again. We see that we get, now this time we get a sum, right? And the sum shows RN1 with the value of 1. That's awesome. We fixed our cyclic problem and learned how to deal with weak references using downgrade and upgrade. And with that, we've reached the end of this video. I hope you enjoyed it, and I'll see you next time. Bye bye.